introduce game of name written with Python. First, the rules of the game. Game of name is played by two players, where each player takes turn to remove at least one stone from one pile only, and the number of piles and number of stones are mostly random. The winner of game is by removing the last piece on the board. The first human vs machine game has been developed in the 1940s called Nemotron. There are many versions of the game developed since, but we'll stick with the original, and with the person who removes the last piece wins. So before we start coding, I would like to identify the variables that decides the winner of the game. So throughout the process, I have identified three most important factors. The first one is starting player, the second one is number of piles, and the number of pieces. So the starting player. The starting player mostly decides the trend of the rest of the game. And we can mostly find who the winner of the game is at the start of the game when the board is first generated. For example, here we have two piles. One pile with one plus stones, and the other one is only one stone. The starting player can just remove all the stones from pile 1 except for 1, leaving each pile have one stone left, and no matter what the player 2 does, player 1 will win. Second factor is piles, number of piles. This decides the minimum moves available and also who the winner is as well. In this example, we have 3 piles, and each pile have one stone on it. So the starting player here will always win because the number of piles is odd. And if we have a even number of piles, for example 4, and each of them has only one stone, then obviously player 2 will win. That is just a basic example, but it explains. And third factor is number of stones. This also impacts on number of moves that each player can make. While the number of stones changes, moves available also changes. In this example, adding more stones to pile 1 and pile 2 also add extra moves for both players. So therefore, if the game is built correctly, AI cannot always win. That is because all three variables are random, and because they are random, then therefore there cannot be a fixed player at all times. So the structure of the software. In this software, I have two major parts. The first part is the board generator, where it will prompt the user interface and the game itself. And then it will be the AI part. The AI part consisted of the algorithm that decides the best move available at the current stage, and it is implemented with Python 3.0. So now we keep that in mind. I have identified a var solution method to find the optimal move at each stage in game. And one of them being NimSum. It is a method developed specifically for the game of Nim. And the other one is minimax and alpha beta pruning. What this is a common game theory that can be applied to many other games, for example chess, tic-tac-toe, and etc. So NimSum. This, by definition, is the cumulative value of XOR of stones of each pile. So this strategy is quite simple. What we want to do is to keep NimSum to 0 when it's the start of other player's turn, which I will go into more details later in the PowerPoint. So the pseudocode, or the basic principle of how my program works. It consists of 5 parts. The first one will be the NimSum. that will be the calculation of the name sum at the current stage, taking the current rock list as the input. Then it will choose the pile to remove from. What this does is it takes a list of piles and decides the most appropriate one to remove from. And find binary. What this does is it will do two things. The first one is to convert each list into a binary number so that it can be decided, so that it's better for the computer or the machine to recognize which pile is best to remove from, and also number of options available from each pile. And then it will be the construction of the game, where all the function will be coded and used to develop an ongoing game for both the AI and the player. And finally, the board generator. This will update the game constantly after each player's turn. So here we go, the main. In the main function, all the implementations of functions will be constructed to compile to run the game. While in each case, we will generate all piles of numbers randomly between 2 and 5 and stone pieces of minimum 2 and plus 1, where all the variables here are random in my software. While the running time for any pile number under 1000 are pretty much the same, we will discuss more about the output. If I have 2 piles, then the command or steps takes for the computer to compute, it will be 2 to the power of 2, and that is under the rule of n to the power of n. So under the rule of n to the power of 2, and that is 4. And if I have 5 piles, and that will be 25, and 100, it will be 10k. And this calculation is, the random complexity of this calculation is mainly just based on the lim sum function, and that will basically decide the time it takes for the AI to decide which pile and which number of pieces it will remove. Okay, now we can go into details into this algorithm. So the XOR operator. The image shown on the left is an example of how it is decided to give it a number under each pile. So here, when we have truth and truth, it will become false. Truth false is true, and then false false is false. And what truth is odd or even number. So for example here, we have pile 1 that have 5 number of stones, and because it's odd, we'll have it as 1, and 1 means true. Pile 2 is 7, and that also be true. And represented with 1 as well. And third pile is 2, and that is even, so we have that as 0. Now with the previous image, here is the strategy of the winning game. In the example here, we have 4 piles with 1, 3, 5, 7 stones separately, and we can rewrite that as 1, 2, 1, 4, 1, and 4, 2, 1. And here we can tell that the nim sum is 0 because all of them are pairs even. For example, if I were to remove 2 from stone 2, then I can decide to remove 2 from stone 4 or from 2 from pile 3. Sorry, but obviously the best option will be remove 2 stones from pile 4, and that still keeping the nim sum to 0 when it's the start of the other player's turn. Now we have the problems with the algorithm. Well, in theory, it really isn't much of a problem because the running complexity of big O n to the power of 2 isn't that much of a problem if we consider all other available all other type of algorithms, because this is relatively quite fast. And I have done testing with I have done testing with 1000 piles, and the running time is really not much different. the output is also is just like instant.